In this video, we pick up the concept of energy. Energy is strongly related to work. So we're going to give a definition. The book gives the following. Energy is the ability of an object to do work. Somehow, the body, if an object has energy, has the ability to apply a force and do a displacement. Now, this definition is somewhat vague, and it's also somewhat misleading, because what really is the case is that work is a way by which energy is transferred from one system to another. But energy, we don't have a good feel for it. So we have a better feel for force and this idea of displacement, and so we can compute work. So we're going to think of energy kind of like it's stored work, but it's not. And we'll talk about later, maybe philosophically, what we say and why we don't believe that it's the same thing, that energy is the more fundamental of the quantities. But this will work for us, and it will help us get the problems done. So think of energy as the ability of an object to do work. And there are two types of energy that we have. We know that if you take an object, say a large rock, and you throw it, then that rock, because it's moving, has the ability to do damage. We know to duck as a child, for instance. Whereas if the rock's stationary, we're not afraid of it because it can't hurt us. So in some sense, by the fact that it moves, it has acquired a property with the ability to do work. We call that energy that it has, that ability to do work, kinetic energy. Kinetic comes from a word that means motion. So kinetic energy is an energy a body has to its motion. And this is really the only true definition for kinetic energy. There's a formula in the book, but that formula is for special cases. What we really mean by kinetic energy is an energy, an ability to do work, totally due to a body's motion. Now, since motion depends on a frame of reference, because your velocity depends on a frame of reference, kinetic energy likewise depends on your reference. You could look at a car and say the car is stationary, but the tree is moving, and there's kinetic energy. Or you could say, no, the tree is stationary and the car is moving. It has the kinetic energy. So there is a frame dependence on kinetic energy. Usually we take the frame to be the Earth, and then we measure the speed or velocity of an object with respect to that. If a particle is moving much slower than the speed of light, then there is a formula, and the formula is derived in your book, and we'll use it a lot, so you're going to want to memorize this formula. It says the kinetic energy, which I have used by the symbol K. Some books use T, but your book uses K. The kinetic energy depends on two things. It depends on mass of the object. So we know that a freight train moving at 10 miles an hour is more dangerous to us than a fly moving at 10 miles an hour. So the more massive, the greater the desire to go in a straight line, the more ability to do work it has. And the second thing is the square of the speed. Now, this is not velocity. These are scalars. So we're talking about how fast it's going. Now, the square of a speed is the square of the magnitude. And with the dot product, that really means that you're dotting the velocity into itself. So the direction is lost and just the length is left and is squared. There's another formula which won't mean anything to you now because we haven't covered this yet. And that's this formula, which can be much more useful in other courses. And even in this course, after we cover the section in the next chapter on linear momentum. It says that you can do it, instead of writing it this way, sometimes it's more convenient to write this as the magnitude of linear momentum, which we haven't covered yet. It's in the next chapter. You take that vector's length and square it and divide by 2 times the mass. Some problems, p is a constant, and so having this constant and having just this is easier. In other ones, you have the mass being constant and you have a velocity. So, or a speed, I mean. So it depends on the problem as to which one's easiest. For us, at least for right now, we'll find the first one, this one right here, as being the best to work your problems in this chapter. So memorize at least the first equation. And you may want to do in the next chapter the second equation. Now, in addition to the fact that an object has energy because it moves, we also know if you take a big rock and you hang it high over our head, that we need to get out from underneath it because you might let it go and it can smack us and do work. This is work the object has not because it's moving when it's hanging above our head, but because of its position. This type of position energy is known as potential energy. Now, in potential energy, it turns out, is only defined for something if it didn't depend upon the path by which it got between 2 points, but just the endpoints. And this is going to lead us to discuss different types of work. So we'll be able to give a more precise definition to potential energy later on. The one thing to note is that while we can give you a better definition, the actual formula for potential energy is force dependent. So unlike kinetic, where I have a single formula, 1/2 mv squared, in potential energy, if I have gravity, I'll have one formula. If I have springs, I'll have another formula. So we have a better precise definition, but we don't have as good of a just one formula fits all. Now, let's talk about what we're doing here. And I'm going to do this by an analogy. Let's say that you had money in a bank. And in this bank, there were two accounts. There was a checking and there was savings. Well, I want you to think of the checking like kinetic, and I want you to think of the savings like potential. You can take money from the potential and move it into the kinetic in the same way you can take money out of savings and move it into checking. The amount of money in savings goes down, the amount of checking goes up. You can take money from checking and move it to savings in the same way you can take energy that's kinetic and convert it into potential energy. You can also take money in and out of the bank, either in and out of savings or in and out of the checking. In the same way, you can add energy to a system or take energy out. You might take some of the energy out of kinetic and some of the energy out potential. One of the main ways to take energy in and out of the system is to do work. So, work is the transfer of energy. That's what work is doing. Now here's the thing. When you transfer this energy into the system and it gets bounced between the checking and the savings, there's no way to actually see the actual numbers on the dollar bills. So how it came in is completely lost. Maybe you put these dollars in and you put them in out of your paycheck, or maybe it was a check that somebody else gave you, or maybe you won the lottery and it came in there. But once it's in here, it gets mixed around, and any information about how it came about is completely lost, and you don't know about it anymore. In the same way, when work is done on a system and energy is moved in, it's not like that work retains its knowledge, its energy, and how it came about is lost. The energy might come into the system, it's kinetic, and it might get transferred over here as potential and come back as kinetic and what have you, but eventually it just ends up being energy, and how it came in and out is lost. So in that sense, it isn't stored work. That's the philosophical argument. Work is the movement of energy, and that how it came about and where it came about is lost. Another way of looking at it is like water. You could have rain, or you could have a river flowing into an ocean. But once the water gets in the ocean, you cannot distinguish anymore whether the water came by rain or whether it came by a river. It's just ocean water now. The river, in essence, being kind of like work, transfers it in and out, but how it comes about is completely lost once it gets into the river. Now, there is some important connections to certain things. We're going to find out that the kinetic is connected to something very important. The work done by all the forces, that net external force we talked about in Newton's law. The work net is going to be connected to putting money into this kinetic energy, this energy of motion. We'll come back to that in a little while in another video. This is known as the work energy theorem, and it's the fundamental theorem of this part of the course. Before I finish this video, though, I want to talk about some other energies that you see. We generally forget about the fact there are atoms inside. And inside a material, atoms can have both kinetic energy and potential energy due to their motion. We call all this energy that's inside a body the internal energy. The kinetic energy of the material, its vibrating in motion, is in fact what people often call heat, although a better name for it is thermal energy. Heat is when energy is transferred due to a temperature difference. But if you heat an object, what you do is raise its kinetic energy. The average amount of kinetic energy, if you take that and divide by the number of atoms, is proportional to a quantity called temperature. We'll ignore the discussion about this internal energy and other things until chapter 13. So for right now, we're going to consider an object like this, like a ball, and we're not going to consider the fact that there are atoms in here. We're going to sweep that under the rug. Okay? So for right now, we're only going to talk about kinetic energy of the whole object and potential energy of the whole object. And if you add those two together, you're going to get what we call the total mechanical energy. All right, that covers this section of the video, and we'll see you on another tape.